connection to GR. So general relativity has many beautiful features. It's useful. It has lots of things to offer both mathematicians and physicists. And well, as far as physics is concerned, it kind of, I think it's safe to say that it's one of the two pillars on which theoretical physics stands. So this is one of the pillars. The second one will be QFT, or quantum theory in general. They are very different, although they have some similarities, but they are mostly very, very different. General relativity has the extra advantage that it's very mathematically rigorous. So it's very clear what's going on there. The usual problem might be with like computational complexity and things like this, but it's like very beautiful and it's very clear what's happening. So this is what I will try to convey today. So I prepared some stuff which is essentially just to quickly summarize what was said before during the preceding things, and also to set up the notation. So I will just go briefly through it. So I call it section 0. So okay, so general relativity is essentially Riemannian geometry plus a little bit of extra words about connection to physics. So at least that's the way I perceive it. So okay, so for us M will be a manifold. Okay, so these are kind of the basic notions that you should more or less be familiar with by now. And if you are not, then just ask. It's manifold. We also seen the tangent space at any point, so I will call it Tm at M. Cotangent space, which is the dual of that. Coordinates, I will typically call them x mu. I will use the Greek indices to label the coordinates. So this is if you have a manifold, then you can have locally some coordinate patch, and it's here where the coordinates are defined. So it's a very local thing. If you have coordinates, then they canonically give you a basis at every tangent space, simply by taking the directional derivative in that direction. So I will call it partial mu, which is short to say partial with respect to x mu. Okay, so if you have some coordinate system, x1 and x2, then these directions coincide with this partial x1 and partial x2. I think I just call it partial 1 and partial 2. Anyway, so and if you have such a collection of bases at every point in whatever your coordinate neighborhood, you call it a frame. Okay, frame is just choice of bases at every point. If you think I'm being too elementary or too fast, then okay. Okay, yeah, if you have a frame, you have a dual frame, simply taking the dual basis. So this is denoted the x mu. This is the basis of this guy. Now, what is a tensor? So, as was said before, discussed, for instance, in the preceding mini course by Olga. Well, one way to look at it is that it's just a multilinear map that goes from a bunch at a given point, I guess M. It's a map that goes that eats several vectors and several covectors, and then it spits out a number. And tensor field, whenever you hear the word field, it just means that it's a collection of such things, but like every point, I have at every point in this neighborhood I choose a tensor, so that's what I call tensor field. It's a collection of these objects at every point. And the components of that, if you pick any frame, then you can write a basis of such things, written like this, using some tensor products, and the coefficients that stand in front of it are what I will call components of the tensor. And here note that, and this was emphasized before, I will use the Einstein summation convention, which means that whenever you see a repeated index, you sum over it. And you will always see in this course a repeated index where once it occurs up and once it occurs down. It's a typical thing that happens in differential geometry. So if you have the same index, and both times it occurs downstairs, then something might be going wrong, so that you better check. So it's actually a very good thing, for checking calculations. But anyway, you really must use this thing in GR, because otherwise you don't get very far. Okay, and as far as, so notation, so I will call C infinity for just functions on the space. I will omit this parenthesis M because I will always have just M, except for maybe like here. Anyway, so C infinity tensor fields of type PQ. So that just means that there is like P times this thing and Q times this thing, or in other words, it means that there is P indices up and Q indices down. That's what the notation stands for. So I will call such tensor fields curly T. in a special case when tensor fields are of type 0 and some number n, and they are completely antisymmetric, then you call them differential forms. This we also see. I will call them omega. This curly, no, it's not curly, it's fracture x, the vector fields. By the way, note that on differential forms, again, as was said before, there is some specific very nice operations. There is this d operator, which takes a form and creates a form which is 1 degree higher. And there is a wedge product, which makes it into some sort of commutative algebra, more concretely, graded commutative algebra in this case. So there is some sort of product here. And on vector fields, you have a bracket, a commutator of vector field, or Lie bracket, or I guess that's the only two names. Okay, so that, okay. And we also saw pullback before. So pullback is a way that if you have a map of manifolds and you have some structure on the right, you can pull it back to the structure on the left. I won't be using this very much, but let me at least say that in particular case when you have a tensor that has only downstairs only indices down, for instance a differential form, then there is a very explicit form that you do. If your tensor was on n was just some alpha, which Britain coordinates had some components and then some couple of dy's, then pulling it back simply amounts to replacing this y by the function y of x, where this f Britain coordinates is written like this, y depending on x. So we just replace y by y of x, and then you take derivatives if needed, so that it expresses in terms of dx. I probably won't be using this anyway, but it's nice to see. And the infinitesimal counterpart of the pullback is the so-called Lie derivative that we also saw before. And infinitesimal means that, well, that is infinitesimal. And here the parameter was a map, and an infinitesimal version of a map is a vector field. So the Lie derivative with respect to vector field is called. Okay. So far, so good. It's just a repetition of what was. Okay, maybe I should swoop. It's just there is nothing new really. That's why I dared to prepare it. Okay, so this we've seen during Olga's course, but let me just quickly go through. So metric, is a special tensor of this type. So it eats two vectors at every point. In particular, it gives you an identification of your tangent and cotangent space. And to see that to see this in practice, suppose that you have a tensor which looks like this. So it has one index up and two indices down. Whenever you see in physics or even math, not this expression, but this expression, where you see that this new index is up instead of being down, and what you should really have in mind is that I use this identification to identify those things. So in coordinates, it just means this thing. I multiply it by g and then sum over sigma in this case. By the way, note that it is for this reason that we are assuming this identification, then one has to be slightly careful with indices. So it's a good practice to keep a horizontal spacing in this way, so that you don't have an index up and an index directly below it, usually. Because, you see, I could just as well have raised the last thing, like this row index. I could have just, replaced, anyway, written a different expression, and I could have raised row, and those would be different things. So it's a good practice to write things like this instead of just cramming everything to the left. Okay. Yes?
So in your example, T mu nu rho, is that a tensor for you, or is it a component of a tensor?
Yeah. No, this is a very wrong abuse of notation. I just wanted to cram as much as possible on this board. So you see, if you have like a T in here, then this T looks like T mu nu rho E mu tensor E nu tensor E rho or something. This is what I should have written. Yeah. And then when you see this thing, this is again a component of a tensor which is now in T21. Thanks. Good point. Okay, so this is okay. Other things that you can do with the metric. You can calculate lengths and areas and volumes and whatever. So for instance, if you have a curve, so curve for us will be just a map from an interval, some interval, into M. Then you can calculate the length of it simply by using the metric at every point. So you have a zero space, you have some curve, and at every point you have a velocity, which we know that it's an element. So this curve is gamma, and velocity at this time will be just the it will be an element of the tangent at that point. Tangent of M. So you can, since it lives in the tangent space, you can use the metric, which is defined precisely there, to calculate the norm of it, and then you do the usual stuff. I put absolute value because I will be also working with metrics which are not necessarily positive definite. So this is just the usual old expression. You just take the vector, take its inner product with itself, absolute value, square root, and then you integrate. So you just chop it up into small pieces and follow the usual logic. Okay, one other thing that you can do with metric is that you can look at isometries. So maps or diffeomorphisms that preserve the metric. And infinitesimally, these correspond to so-called killing vector fields. So killing vector field by definition will be a vector field. So
I think you don't need the square, because it's already G gamma.
Ah, thank you. Yeah, good point. Thank you. Was it the same?
Yeah, thanks.
Fair enough. Okay, so there might be a typo in the lecture notes, possibly. Oh yeah, there is lecture notes, by the way. Yeah, so there is a on the school website there are lecture notes for these. I should have said this before. So supposing if any one of you gets bored because you've seen this stuff many times before, or for whatever reason, then you can look at the lecture notes. I put in lots of exercises in, so you can try to go through them. Some of them are easy, most of them are, I guess, medium, and some of them are hard. It's not. I didn't distinguish them, so it's just a bunch of exercises. Yeah, so just feel free to look into them if you are bored, and I'm happy to help you or give hints if you need anything. There is one typo in one of the notes that I talk about it. I noticed that in one of the last exercises there is this relation between scalar curvature and the Gauss curvature, and I wrote that it's k/2, while in fact it's 2k. But it's not a big thing, and you would spot it anyway. So this is just a completeness. Okay, where was I? Right, so killing vector field. So killing vector field is an infinitesimal counterpart of an isometry, and explicitly just it's a vector field such that when I take the lead derivative of the metric with respect to it, it's 0. Okay, I'm saying that because I will come to it later. Okay, now as for the things we've seen most recently are the connections or covariant derivatives. So just to recall, so these are maps that eat two vectors. Vector fields, and spit out another one, usually written in this way. And you want some things from them. You want that this is bilinear with respect to real numbers. You want that in this first slot is actually tensorial. So if you put a function in there, then you can take it out. So if you activate this on a vector field y, then the vector field you get here is the same as vector field here multiplied by this function. And finally, you want this derivative property that, if you multiply the second slot with a function, this is a function f, same infinity. Then you want that it's not tensorial there, but there is a derivative term acting on f. This is kind of important. And you can extend this by so far this connection was something that acted on a vector field, y, but you can also let it act on other stuff, for instance on functions, where you just simply define this to be the action of a vector field on that function. So this is what I mean by xf, vector field acting on f, so the derivative of f in the direction of x. You can also let it act not on functions, not on vectors, but covectors, or tensors of type 0, 1, simply by this kind of usual stuff that, if you have an alpha in here and you want to know what the nabla, which is the name of this symbol if you haven't heard it before, nabla \nabla. So yes, you simply define this by this formula. It's like kind of using the Leibniz rule that you want this to be the same as if you would apply this thing to the whole pairing of a vector with a vector. function minus nabla x acting on the vector. Okay, and you can extend this to any tensor field simply by Leibniz rule. So by requiring that it distributes over in this way over, not distributes, sorry, it has this derivative property with respect to the tensor product. And you can check that it's nicely consistent and everything. So, okay, so this is connections. And just if you ever need to work with them explicitly, then if you pick a coordinate system, then you define Christoffel symbols by this formula that we've seen. I think so. So you just look at what it does. You take special, as your special vector fields, you take the coordinate vector fields. So partial nu, partial rho. You take the derivative, covariant derivative of partial rho with respect to the partial nu. And you get, again, some bunch of vectors. Expanding them in the basis, you get some coefficient functions, and those are called Christoffel symbols. So there is, unfortunately, as Olga mentioned, there is multiple conventions for these. So I will, well, first of all, there is different conventions on how you order indices there. So I will use this one. Second of all, there is, you can call them Christoffel symbols in various circumstances. So I will follow, I think, Wikipedia or whatever, which says that these are defined for the case when your basis here is a coordinate basis. Okay, so in principle, you could just take a general frame, and you put E alpha, EA, EB, whatever. But okay, it doesn't really matter. But anyway, I will use the setup when there is a coordinate system. Okay, and the curvatures. So suppose that you pick two vector fields. Then you can define this curvature operator, which again, as we've seen, was just some expression like this. It acts on vector fields, create a new vector field. And in slightly surprisingly, if you haven't seen it before, you can in fact check that take three vector fields x, y, and z. And this expression here is function linear in all slots. So if you take if you put a function f, let's say, multiplying this vector field y, you can take it out. There is no derivatives on it. Which just means that this is a pointwise defined object, and hence a tensor field, sorry. So a tensor at every point. This is called the Riemann tensor. By convention, I will call its components like this, because here it again matters how you order the indices. And one last thing that I prepared is the torsion. So torsion of a connection, that's a concept defined for any connection. So fix a connection, then you define torsion to be this map that takes two vector fields, creates a new one, and this is the explicit formula. Now again, similar to the curvature, it's slightly non-trivial but not difficult to see that this is again a tensor. So yeah, it's a tensor. It eats two vector fields, produces another one, so it's a tensor of type 1, 2. Okay. Whew. Okay, so far. So good. Okay, okay, any questions? No questions. Okay. Okay, yeah. So, okay. Just to finish, there are a couple of more things that that I should recall. So, yes. So, as we saw during Olga's mini course, then there is this fundamental theorem of pseudo-Riemannian geometry, which says that. Okay, so let's say fix a Riemannian or pseudo-Riemannian manifold M and with G. Okay, pseudo-Riemannian just means that it's not positive, not necessarily positive definite. Okay, so theorem which said that there exists a unique. Okay, I don't know. Do you use this notation? There exists a unique thing. Okay, there exists a unique connection. Blah blah, such that its torsion is 0 and metric is covariantly constant. So this is the same as to say that this thing is 0 for all vector fields. So there is, if you have a Riemannian or pseudo-Riemannian manifold, then you get for free some extra structure, namely you get a connection. A particular chosen one. So this one is called Levi-Civita connection. And you can even write an explicit formula. That's kind of beautiful. So if you pick any coordinates, mu, you can write explicitly what this gamma mu nu rho is. 1/2 E mu sigma. This is just to say that there is an explicit formula for it. Okay, so where again, so this just means partial derivative of these coefficient functions, and this thing, whenever you see metric with upper indices, then it means that's by convention the inverse of the metric. And okay, so from now on, whenever I talk about connections, I will mean Levi-Civita connections. Okay, so I will not assume as an extra datum. I will just say that okay, I will just suppose that you have a manifold with a metric, and nabla will always be the associated Levi-Civita connection. And then you can show that in such cases. So okay, let's go with proposition. Okay, let me write it in this way, because I think there is you can benefit from it if you haven't seen it before. So if I lower the index on the Riemann curvature tensor, so that I get some tensor of type 0,4, okay, I will write the following thing, and then I will explain if you haven't seen this notation before. This is probably the notation before. Okay, so this is, in all cases these are A, B, C, D. I don't know if you can read my handwriting, but okay. So what does this mean? So presumably not all of you have seen this. Okay, very good. So so this is another useful convention that comes similar to the Einstein summation convention, but probably less widely used. So anyway, so whenever you have an expression and you have some bunch of indices and you put these square brackets around them. So if you have an expression, something, and then you have some, let's say, A, B, C, and then you go further. So imagine some expression, like for instance, like this. Then by definition, this means that you are taking the complete antisymmetrization with a normalizer. So how to say this? So if there is 3 indices, this just means that I will put 1/3 factorial, and then I will write the same expression, so whatever was there, and I will put A, B, C. Then I would write the same expression again. I would put A, C, B. So I will sum over all the permutations, and I will put a sign depending on the parity of the permutation. This one plus B, A, right? B, A, that is B, C, A, etc. So there is 6 things overall. Okay, so for instance, this thing. Okay, I don't want to write 3 things. So let's say this thing here. Is just by definition 1/2 of R A B C D minus A B A C D. So the beauty of it, including this prefactor, which is important, is that putting this square bracket serves as a sort of projector operator, in the sense that if the stuff was already antisymmetric, then putting square brackets on it will just not change anything. See if this, because I mean, so anyway, maybe an exercise to think about. So, by the way, okay, so I can do the same thing exactly with round brackets. So this I define to be the same thing, but it's always with a plus. Okay, so this is just sum over permutation and not counting the parity. So in all the cases this is just sum over the permutations. Okay, so now question. So suppose that I have a metric GAB. Now what is this thing equal to, and what is this thing equal to? And so this is a question. If you've seen this before, then don't answer. So what are these things? I will give you moment to think about that.
The first is equal to itself because its metric is symmetric
Exactly.
and another is 0.
And the second one is 0. Okay,
Yes, so this is
just 1/2 of GAB minus GBA, but since it was symmetric, it's 0. And this one is GAB, 1/2 of GAB plus GBA, but because of the symmetry, it's the same thing. Okay, so whenever so for instance, the first equality here, how should you read it? This thing says that if I antisymmetrize on the first two indices, it's the same as if I wouldn't do anything, which just says that that this expression is actually antisymmetric in AB. Okay? Because if I antisymmetrize it, it stays the same, so it has to be antisymmetric. So the first equality says that this Riemann tensor is antisymmetric on first two indices. The equality of these things means that it's antisymmetric on the last two indices. And equality here, okay, this just means that it's symmetric under the exchange of these pairs. And this thing is the thing, as we've seen again before, this is the algebraic Bianchi identity. Okay, yeah, this is just a useful thing to know. It really simplifies your life. Okay, so now that we have defined everything, okay, almost everything, we still need to have a couple of other tensors. So, okay, should I do this? Okay, so again, fix a Riemann in manifolds. And now we define the remaining tensors. So we define the Ricci tensor. To be just the contraction on the Riemann tensor. So note that if I talk about components, then it's kind of clear that this thing is, that the Riemann tensor is different from this one because one has 4 indices and one has only 2. Actually, sorry, let me not use Greek indices, but let me put this with Latin indices, just to emphasize that this is a arbitrary frame, not just a coordinate frame. Anyway, so if you have a Riemann tensor, you can contract it on 2 indices, and you get the Ricci tensor. Now, if you haven't seen contractions before, then this really just means that you sum over all such things. And you can check that this is actually a coordinate independent or frame independent statement. So taking contractions, that's an exercise to check if you haven't seen it before. This is independent of the basis. So it's a well-defined operation on tensors. So overall, this thing defines a tensor of type 0, 2. And note that actually for this I didn't really need the metric. I could have just done this for any connection. Because if I define Riemann, this was discussed before, just contract it. But in our specific case, I will fix a Riemann metric, and I will take the nabla to be Levi-Civita. Okay, and finally, the scalar curvature. Will be now the contraction of this guy with the metric. So this one really needs to use the metric. And so this doesn't have any remaining index. So it's 0, 0 type tensor, which is the same as a function. Okay. Okay, any questions? So far this was just a very brief reminder. Now let's do something new. No questions?
Just for the fun of it, since you seem to care, like when you lower the index in Ricci, you put it on the first place line.
Ah, very good. You mean?
So your definition of R with all the lower indices, no, not there before, when you discussed symmetries.
Ah, yeah, okay. You mean why did I contract first and the third?
No, why when you lower it with the metrics, you put it on the first place? In principle, you can choose any convention.
I mean, why isn't this RBA? No, that's
I
not.
mean, why it's R A B C D, not R A C B D or something?
I talk about the Riemann.
No, not this one, the previous one, but similar. So
Ah.
four indices.
Oh, why? Oh, you mean why was it like this? Ah, that's a very, you mean this equality?
Yeah,
That's a very good question.
I'm not sure it is. It's probably conventional, but just.
Yeah. This is yes. I don't really like this convention, but it's kind of so definitely you want to group these two guys together, so that you want them to see that this is just some rationale behind this. Why did I choose this particular permutation? So you want these guys to be together because that's how we define the curvature operator. You want them to be wherever but together. And the other two things you can, I would maybe rather like to define this thing as CD and then AB. Fortunately, those two things are the same in the Levi-Civita case because of the symmetry that I erased, because of the swapping of first two and last two indices. So I think in like gauge theories, this is the more natural thing to do actually. But here, fortunately, it doesn't matter because they're equal. But yeah, this is a good point. Like
Just having in mind some supergeometry. That's there.
yes, but
Okay, no.
This is simple.
I leave you in peace.
yeah, thanks. Actually, I want to erase this. Okay, very good. I see everyone is happy, so let's go further. Okay, so this is just a remark that might seem a bit annoying, but I find it kind of important. So note that. Very good. So in this definition, the fact that the connection is actually function linear in the first slot, so the fact that whenever you act with this is the same as with acting with nabla x and then multiplying by function, this thing actually says that if you have a tensor that was of some type, like PQ, then you can see nabla t as a new tensor, which is one index more, one lower index more. Okay, simply by saying that this new tensor, if you feed into it a vector and then whatever, this is the same thing as doing this thing, and then having the resulting tensor, feeding it with whatever was left. Okay, so another natural and equivalent way to look at connections is that it's something that, it's a tensor, like here, you have a tensor like this, and you let your nabla on it, and it creates a new tensor which is one index extra. So, and you can repeat this, so you can have like, nabla many times on T, and if this was like n times, then this thing will be P and Q plus n. Now, why am I saying this? Okay, so because now we can make a nice definition. So tensors of this type, I will give their components a special name, so not special form. So if you have such a thing, note that downstairs I created n extra indices, so I will have some n new indices in here, and then I will have whatever, like if T was a tensor which had, I don't know, some structure like this. Okay, this is just schematic. It can have whatever tensor structure. Some can be up and down, and you can horizontally move them, whatever. I will just, whenever you have this new tensor, this big one, and these components, I will define this to be just, sorry, the other way around. I will define the expression on the right hand side. Okay, so okay, yeah. So this is a relatively subtle, mild and subtle point, but I think it's worth to emphasize. So whenever you see an expression like this, namely that you don't feed in your nabla vector fields or whatever, but you have indices there, what you should think of is that it's really this, that you just had a tensor, you let your nabla on it many times, you created a larger tensor, and then you take components of this. And so, if you don't see why this is subtle, then the point is that you can have, for instance, if you have a vector field, x, a vector field, then you can have an expression like this, which follows this philosophy, which is just a component of this. You can have stuff like this, and you can have stuff like this, and all of these guys are different. You see, this thing means that, I mean, if I really am like purist and I'm really following the the directions that I have, so this thing is just a component, so this is a function, it's a component of your vector field, and then I'm differentiating it in this direction, and I'm differentiating the result in this direction. While in here, I take the the vector, I take a covariant derivative of it as a vector, then I take the covariant derivative of the result, and then I take the C component of that. And this thing was that thing above. And the advantage of this guy is that this thing is much nicer than the other two expressions, because this thing forms components of a tensor, namely this tensor. Okay, so potentially I just confused some people, but it's always good to be confused. Okay, so just like, just formally following the logic, these things are really different, and what you normally want to work with is, well, it actually depends, but I mean, you typically definitely don't want to have expressions like this. But yeah, these two are nice, and this one is especially nice because it's components of a tensor. Okay, so just to see that just maybe to give you one example that we can try to derive, is that, okay, so again, assume that nabla is Levi-Civita. Then you can have this nice formula. Nabla A, nabla B, xc. So this follows this logic. This is this guy. And maybe just to clarify, so this expression on the left-hand side, this is just a shorthand for saying that I take nabla A, nabla B, xc, minus nabla B, nabla A, xc. It's not of this type, because I did not use commutator on the indices, but this thing that I discussed here, this was only valid for indices. If you use symmetrizers or anti-symmetrizers for indices, yeah, it's kind of confusing. Whenever you see this bracket, then this really means one minus the other, unless I'm talking about indices. Anyway, there is this formula. It can be contrasted to, yeah, very good, still here, with the appearance of Riemann tensor, as we saw in the definition, but this thing is kind of shorter. It doesn't have this extra term. If you think about it, that's kind of the beauty of working with these guys. Anyway, you can try to amuse yourself with proving this. This is sometimes called the Ricci identity. There is lots of identities in Riemannian geometry. And some of them carry different names depending on who you ask. Yes, yes?
Shouldn't be the index of the vector field on the right-hand side be a D?
Yes, thank you very much. Yes. Thank you. Good point. For all vector fields. Any other questions or any other mistakes that you spotted? Okay, if not, then this is the end of part 0. Now let's talk about some fun stuff, like what can we do with the Riemannian geometry. So it seems that it's kind of, so far we've seen lots of definitions, so if you haven't seen them before it might be a lot to absorb, but fortunately it's been kind of spread throughout the day and the week, so hopefully that's easier. So okay, let me talk about geodesics. That's one of the beautiful So what's the idea? So let's start with the following observation. we are on a Riemannian or pseudo-Riemannian manifold, and you have a curve. So just as before, this is a map from some interval into M. Okay. In the pictures, it's something, you know, something whatever. Then we already know what the velocity is. Velocity is simply, you know, you look at your curve and you look at the tangent vector at that curve at that point. This is the velocity, and before we called it gamma dot. Dot being the usual notation for time derivative. I think this is due to Newton, maybe? The dot? Who knows? Who studied the history of physics? Is it? Is it? Okay, very good.
I'm not sure, but it might be.
But you, okay. Or did you want to ask something, or?
No.
Okay. So we have a curve. The velocity is just, it's clear what it is. Now, the right notion of acceleration, so acceleration, remember, is just like a second derivative of your position. Acceleration. What really you should think of an acceleration is this expression. It's nabla gamma dot, meaning that at every point here you have a definition of your gamma dot, you have a velocity, and you want to see how it changes with time as you go along the curve. And the right notion of differentiating things that are not at the same point but are moving is using the nabla. So this is kind of the right notion of acceleration. So this is the observation. That the Riemann manifold, when you want to talk about the acceleration for some curve, then what you should really think about is this. Okay, now, does anyone see any obvious problem with this expression that I wrote?
Non-locality.
In what sense?
Different. I mean, in the expressions there enter different points.
I think it's related, but this should be fine. Like this covariant derivative is precisely for identifying things that sit at different points. So the problem there is that when I defined the covariant derivative before, then it needed to eat a vector field. Now, if I only have a curve, then this gamma dot is just a set of bunch of vectors which are only defined along the curve. So why is this a meaningful thing? Okay, check. Anyone sees why? Okay, I'll write it anyway. So, right, so let's suppose that we have a covariant derivative explicitly. So if we have two vector fields, x and y, then if you really write what this, so this is a vector. So if you look at it, its smooth component, and you break it down, then this is what it looks like. If you really write it in terms of the components. Okay, so now, so what is this? So now I have my space, and I have two vector fields, and I have, well, the second one. I have two vector fields defined everywhere. Now, if I'm interested in calculating the covariant derivative and looking at this result at some point, like a particular point somewhere at M, then what are the ingredients on the right-hand side that I need to calculate that? So first of all, I need to know what. Okay, so let's say at point M, let me put a subscript. So I need to, okay, whatever. I need to know what x was at M, I need to know what y was at M, at point M, I need to know what these guys were, but these guys fortunately are just fixed because they start with the Riemann manifold. So as far as the data of x and y that I need to use in order to calculate this, I really need just the values of. I need at M to know the values of this guy, the values of these guys, and there is only one derivative information that I need to know the derivation of these components of y in the direction of x. Okay, so this, if you think about it, this is really just like a directional derivative of these components. Okay, so these are the only three things that I need to calculate this. I need to know what the value of these things was at that point, and I need to know what the derivation of this y was in the direction of x. But this, I have all of that in here, because I'm taking here, I start with a curve, which means that I know its value. At every point I know what the velocity vector was, and I also know, what this derivation was, because I only require to know the variation of this vector in the direction of here, which I do have because I have it along the curve. Yes?
Sorry, I think the other person has also already mentioned it, but here when we write the nabla of gamma dot by gamma dot, that is a bit, or I mean, there's a little subtlety that gamma dot is not really a vector on the interval, right? Or if the tangent space of the interval, technically we would need to use like a dt or like a tangent vector on the interval, because the covariant derivative of a vector field along the interval should also eat vectors along the interval.
But here I'm not. This is a nabla on this manifold itself. It's not. It doesn't use the interval. It's like in general.
Gamma dot is a vector field that eats interval values and spits out tangent vectors on the manifold, right?
Is a tangent
Well,
vector.
yes, but
At every point t.
yes, but you can also just as well see there's a bunch of vectors defined along a curve.
But then you have intersection points where it's not really clear, right?
Fair enough, but yes, but
Like you cannot replace gamma dot by a vector field, otherwise you run into some troubles on
The curve is regular.
in this case you can actually. I mean, to really know what this thing is at. Okay. So the resulting thing here will again live at only on the curve, and if you look at a point on the curve, namely gamma of some time, it's a gamma tau, then this thing here will be calculating using how should I say it? Now this kind of information. So you need to know what gamma dot tau was, and you need to know what the derivation of this vector was in the direction of gamma dot tau.
Wait, Fridrich, you don't have intersection points, do you?
Sorry?
There are no intersection points. It's not self-intersection.
I mean, you can have curve that goes like this. Like the intersect is okay. Now it intersects.
So you will have this
Oh yeah, of course.
so far.
Yeah. I mean, you can have a curve which is just constant. That fits in with the whole thing.
Go on.
Sorry?
Go on.
Okay, so
Let's come back to it.
anyway, we should make a break, but let me at least finish this point. So, okay, okay, let me just restate differently what I said here. I hope it will answer the thing. It's just that in principle, all that you need to calculate. So, although I said that you really need like proper definition is the standard vector fields, and you need them to be defined everywhere. What you really need is that it's enough if you have a space and you have a point and you have a vector field sticking there, and then you have a curve that passes through it, and you have a vector field defined along that curve. So the first vector is x, and the second one I will call it y. And then it's meaningful what it means to have nabla xy. Do you agree with that? And right, so in this case, what I mean is that you really just you have your curve and you can intersect or whatever, but calculating the acceleration at this point, the only thing I do is that I use as my x the thing the tangent here, and I use as y the field gamma dot, but which is only defined along the curve. So it's an expression of this. No, where was I writing? Here. It's a stuff of this type. Okay, let's make a break and let me think on how to say this differently.
Yeah.
Okay, welcome back. So just to summarize the resolution here. When you have a curve, then you can make sense of this as a meaningful expression. Simply because it's following this what is the only data you need is what blah, blah, blah. You can also do it more formally by using by looking at kind of the, still here, the pullback. But it's also, in terms of formulas, it's also very meaningful to do it as I namely just write down what it is and then substitute it. So it's a meaningful thing. It's just to okay, so anyway, okay. Very good. Okay, so now we can make. Now that we know what an acceleration is, and you might remember from some whatever physics that like if you have stuff that has no acceleration, then you should think of it like a free moving stuff. There's no forces acting on it, and it's like zero acceleration. So the bottom line is that the curve, there is a special curve. The special class of curves. So we call a curve a geodesic. A geodesic is a curve gamma from some interval, let's say AB, m such that its velocity vanishes. So you should think of it as so there is like no forces acting on it. Yeah. So if you write it down using this formula explicitly, what it means. So you pick some coordinates. Okay. So some remarks. The first remark is that if you pick coordinates x mu, then you can write down very explicitly what the equation is. For that equation is, and it looks like this: x double prime double dot. Remember, it's just the derivative with respect to time. Time is now the parameter of the curve. This thing plus gamma mu rho x dot nu x dot rho equals 0. So this is an ordinary differential equation or set of ordinary differential equations. So you can argue that this has a solution at least for some short time. Also remember that these, strictly speaking, these Christoffel symbols, they depend on where you are on the manifold. So they themselves depend on x. So x is hidden not just in here, but also in here. And solutions to that equation are called geodesics. Okay, so now, let's say remark number 2, small proposition. It says along the geodesic, the square of the velocity is preserved, or the norm of the velocity. Square of gamma dot is preserved. So how do you show this? Little half-line proof. So what does it mean that something is preserved? It means that as you go along the curve, it doesn't change. What does it mean to, if you want to, so what is the quantity that we want to see? It's the square of the velocity. So, so that by that I just mean, this thing. It's the square of the velocity. Take the square root, it's the norm. And now I want to see how this thing changes along the curve, along that curve itself. So what is that? I mean, I just use I use the covariant derivative connection in direction of that. So this is what I use when I measure quantities along the curve. Okay, but now, of course I erased it, but anyway, recall that this is now a Levi-Civita connection. So Levi-Civita, one of the things was that nabla G was 0. So if you act with nabla on G, then it is 0. So if you, there should be a big parenthesis here. So you can think about it in more detail, but essentially what it boils down to is that this thing, it acts again in its way, so in a derivative way. So this thing either differentiates G, which is 0, or it differentiates gamma dot, which is also 0. Or it differentiates the other gamma dot, which is also 0. So this is 0. That's the end of the proof. Okay. Yeah. Now, sometimes it might happen. So, okay, remember that curve for us is really a map from this to this. It's not just the shape. It's not just the, it's not just the shape itself. Like if you have something like this, that's not a curve for us. For us, a curve would really be a map from, map from here to here, so that I keep track of the parameterization. And this equation is kind of dependent on, this is all done in some specific parameterization because this dot is the derivative with respect to the parameter here. So all I'm saying is that curve really is this full information, and not just the image of this gamma. Okay, so now it might happen that if you take a geodesic and you reparameterize it, meaning that you choose a different, let's say, okay, so suppose that instead of gamma, I replace gamma by gamma precomposed with some map phi, where this map phi is a diffeomorphism from the interval to itself. Okay, so this is just a fancy way of saying that I reparameterize this interval. I choose, like, instead of parameterizing, I just use a different map which has the same image, same curve, but it has a different parameterization. So if you do such a thing, then what previously was a nice equation, so if you start with a geodesic and you reparameterize it, then suddenly it will be slightly nastier. It will look something like this. There's some function times gamma dot, where this f is now a function from the interval to numbers. Okay, so nice equation, not so nice equation, but still kind of because it's not terrible. Now, okay, so the moral is that, like, if you have a geodesic, but you choose a wrong parameterization, some nasty one, then the equation will look more complicated. But fortunately, it also works the other way. That if you ever encounter, okay, so this is a converse statement. It's just a consequence of some ODE, existence uniqueness things. If gamma solves this equation, maybe I should have, okay, let me call this gamma prime and then claim that this is for gamma prime. Okay. For gamma, we have this, and for gamma prime, we have this nasty equation. So conversely, if you start with here, so if you have like gamma which solves this thing, then the claim is that you can then there exists a reparameterization such that it will look like this. So you can define some gamma prime. Okay, now I'm exchanging the rows of gamma and gamma prime together, such that the new gamma prime will satisfy the geodesic equation. Okay, so the moral of this is that this is the geodesic equation, but also if you ever see something that solves this equation, that's also a geodesic. It's just a geodesic in a wrong parameterization. Okay, this will be important in a second. The following propositions. Proposition. Very straightforward to check, so I will leave the proof to you if you're interested. It's one of the exercises in the sheets anyway. So the geodesic equation which I just made is the Euler-Lagrange equation. I will explain what I mean. Equation for the following action function now, for the following. So given any curve, I can calculate the following expression: 1/2 of g gamma dot d tau. Okay, so now remember gamma was a map from A, B, M, and I will call tau the coordinate in here. Okay, so I erased it, but okay. This looks very, very much like the thing we saw before when you measure curves, except when you measure curve, there was a square root. And there was also the extra square that I forgot as you pointed. So this is different. It's a different equation. There is no square root. In a sense, this looks very much like kinetic, like usual action functionals in physics. In that there is no square root and it's second order, whatever. means a square. Okay, anyway, so this is the end of the claim. So now what does this mean? If you don't know what Euler Lagrange equation just means that it's you have such a form, you have such a quantity which is defined, this S is defined for any curve. And now the statement that this is an Euler Lagrange equation just means that the curves, that the extrema of this functional are given by this equation. Okay, so Euler Lagrange equation is just the okay, so in other words, geodesics are extrema of this functional. Okay, and you can check this. It's not difficult to verify. For instance, by writing explicitly this thing in terms of Christopher's. It's very straightforward. But now, why is this interesting? Okay. It's interesting because this thing is a very nice looking stuff. And okay, so let's say use of this fact. So you can use this thing to actually extract the Christoffel symbols very easily. Okay, so since this is a mini course, I was not, I was going rather fast, so you didn't have time to absorb the fact that these Christoffel symbols are actually horrible objects and it's super painful to calculate them. So there was a formula at the beginning how it looks like in terms of metric. And if you have a specific metric and you want to calculate what these things are, it's straightforward, but it's super horrible. You can use Mathematica or whatever, some software to do it. But usually it's painful. But there is a nice and easy, there's an easier way which follows this thing. So let me illustrate this. Okay. Okay. Let me just put it differently. I write down an expression like this. Then I try to look for extrema of that. I find them out. I will get some differential equation, and then I realize that differential equation is just this differential equation, and I can read off these symbols from it. Okay, so example. S2, seen as I use the opportunity of the break to draw this figure. So imagine that this sits in R3 as a unit sphere. And then we saw before that the metric on such a thing, if I take coordinates theta and phi, so I have a point here, this is the center, this is theta, and if I project it down to the plane here, then how does this work? I use this angle is phi, or something like that. The important thing is that I know what the metric looks like, and it looks like this. I obtain this formula simply by pulling back the metric to that sphere sitting in R3. But I will just use the formula because we've seen it before. Okay, so I have this. So now so what does it mean to have a curve in this setup? So I have a curve. Okay, this is what it means to have a curve. Okay, curve. And I can parameterize this curve in terms of so this is the same as essentially describing how the coordinates depend on time. I call time tau here, unfortunately. Okay, so let me stick to that. Okay, and if you calculate the gamma dot explicitly, then in terms of these things, it will look like, if you think about it, it looks like gamma theta dot multiplied by partial theta, and phi dot multiplied by partial phi. This is the curve. This is the metric, so I can calculate now I can write down the action functional explicitly. Okay, so what is this action functional? Gamma. Okay, so I just use this thing as my gamma, substituted here, and I use this metric here, and you can easily see that what you get here is an integral of theta dot squared plus sine squared theta phi dot squared. Okay, this thing is theta. Okay, it's you literally just plug this in here, and you just pair these d thetas using the first term and pair the d phis using the second term. Okay, so now you have this action functional, and then if you're a physicist or if you followed some calculus of variation or something, then you can find out the extrema of this functional. And okay, let me just, that's a small calculation, but okay, it's essentially, okay. Now, okay, should I skip this? Okay, yeah, okay, let me just write the result. So the resulting extrema of this, which is just like one line calculation, is that theta double dot minus sine theta cos theta phi dot squared equals 0. That's one. And another one looks like phi double dot plus 2 cos theta over sin theta dot phi dot equals 0. Actually, if you really write down the Euler-Lagrange equations for this, then the equation for phi will not look like this immediately. You have to, it will look slightly differently, but this thing will be multiplied by something. But you know that you want your stuff to have this form precisely so that you can read off the Christoffel. So if you divide by whatever was in front of here, then you get this thing. So this is the set of equations. And now just using this general formula, you can immediately extract the Christoffel symbols. So this thing tells you that there is only 2 or 3 Christoffel symbols that are non-zero. The first line tells you that, comparing it with the equation, is that gamma theta and then phi is simply minus sin sine cosine. And the second line tells you that gamma phi upstairs, theta phi, which is actually the same. I didn't mention this, but the Christoffels are symmetric, so this is the same as the other order, is cos over sin. Without the 2, because in here, since this thing is symmetric in nu and rho, I get it once like that and once in the other way. So there is so that's why there is a 2 over there. So those things are without the 2. Okay, so that's it. This is the Christoffel symbols for, yes?
I have a question about this trick. Like, this only works for diagonal metrics.
No, it doesn't.
Okay, but if the metric isn't diagonal, then maybe the equations don't decouple. There's for example, a theta dot phi dot term.
The phi dot, yep.
Then I vary, and then I will need to partially integrate. I will have like an extra term, right? So the Euler-Lagrange equations are not like.
You mean that you will have a sum of like one double dot and other double dot?
Other double dot,
Okay.
and then they're maybe not as useful, or can I manipulate it somehow?
No, that's a very good point. Yeah, I kind of forgot about that. Yeah, so the point is that just you did have a couple of equations, and then you all write them in a way that each one of them only contains one thing double dotted, and then you can read them off. If you have like an expression where you would have theta double dot and phi double dot, and then there would be a second equation where they would be somewhat different, and you take a linear combination such that you kill.
Ah, okay, sure.
Is that right?
Maybe. That makes sense.
Sorry?
Okay, that makes sense.
Yeah, I mean, to be fair, all the exercises that I ever did were diagonal, so that, no, this thing never arose. But yeah, that's a good point. Yeah, so you might need to do some non-trivial work to actually kick it into this form, but yeah. Okay. Yeah, okay, maybe it's more subtle than I thought, but anyway, it's a useful trick to know. Okay, so, okay, by the way, now small exercise. So can you see any, so remember, geodesics are solutions to this. So can you see any, I'll give you a couple of minutes, can you see any geodesic which is of this form, that phi is constant for some value, let's say phi 0, and theta is not constant, or the other way around. The second case is phi depends on tau, but theta is constant. 0 just means it's constant. So can you see any solution to these equations which have this form? That either phi is constant or theta is constant. So you can look at it.
If theta of t is linear, the top one is at least solved.
Well, yes, but is it necessary for it to be linear? Yeah?
How about the phi?
question is essentially if there are some nice geodesics on this sphere, which incidentally roughly coincides with our planet. Yes, yes. So which ones are those?
Well, the first one, if you look at the first equation, you put in the phi, which is constant. You have the second derivative of theta, and you get a linear function. It means that the angle theta goes like
Very
that.
good. So thank you. So if phi is constant and the second equation is just vacuous, it's automatically zero. This thing falls away, and the only thing is theta double dot is zero. So this thing, yeah, I can take this to be anything linear. And what does this correspond to in terms of the picture? It just means that I fix the longitude. I fix some angle here, and I go like from North Pole to South Pole, and then potentially back. It's like these great circles on the passing through the poles. So that's the case number one. What about the second case?
Well, for the second case, you look at the second equation. There you have dot of theta, which is zero. That you just have the second derivative of phi, and so you have another circle. Well, phi is rather.
Yes, but there is a subtlety with the first equation.
Yes, and first. Yes, and yes. No, well,
So let's see what the equations are when I plug them in. So in the first case, I get if theta double dot is zero, phi double dot is non-zero. So I get like sine theta, cos theta, phi dot square is zero. That's what remains of the first equation. And now the second equation, because theta was constant, the second term drops out, and I get that phi double dot is zero. Okay, so the second thing tells me that it's linear, as you were saying exactly. So AT plus B, A tau plus B. But we see that in order to satisfy the first equation, this can only be satisfied if if either phi dot is zero, meaning that you are standing, which is technically also a geodesic, or if phi dot is non-zero, then you need to have a vanishing sine of theta or cosine of theta. Okay, so this is only possible if theta is in 0, pi half, or pi, which makes sense because then it's the equator, or it's just these points. And the point itself is always the geodesic. And you can see that it nicely matches, that you don't have any geodesic which would go like this, because that's not a you should think of geodesic as curve which is like go as straight as possible, and this thing is not really going straight if you think about it. Okay. Very good. Perfect. Okay, so now we have one proposition. So there is a second proposition, which is very similar to the first one. Second proposition, very similar. There is a second action function now. So the Euler-Lagrange equations, which is just a fancy way of saying the conditions for the extrema. Euler-Lagrange equations for the same function now, but with a square root, for integral from a to b square root of, and okay, let's put the absolute value there, d tau, which you might recognize as simply the length of the curve, calculated with respect to this. So the Euler-Lagrange equations for this guy have the form, unfortunately these are not geodesic equations, but they will look like this. So this thing. And by our preceding discussion, we know that this is actually a geodesic in disguise. It's just geodesic with a potentially wrong parameterization. Okay, so in other words, so In other words, the extrema, or like length extremizing curves are precisely geodesics. This is often how you see geodesics introduced. They are like things that extremize the length. Precisely geodesics up to parametrization. So the shapes that you get here are definitely geodesics, and you just need to play a little bit with parametrization to get rid of this annoying F. Parametrization. Okay, you can see this working here. That if you have a sphere and you have 2 points, then the shortest curve in between them is the one that goes along along like this red line, for instance, like this. What is called the giant circle? Giant.
Great circle.
Big circle.
Big circle. Really?
Great circle.
Great circle. Thank you. Yeah. That sounds much better than big circle. That's here. Yeah. It's okay. I shouldn't. It's great. That's not what I wanted to say, but also very good. Okay, so now a question. So notice that I use the word extremizing, not minimizing. So can you think of a geodesic which is actually not the local minimum? Or are they always local minima? Are there geodesics? The answer is yes, and you can just look at this the sphere to find examples. So can you see any example of a geodesic that on a sphere that actually is not a minimum, just an extremum of the action functional? Yes?
If I take 2 points, there's clearly the minimizing geodesic between them, but I could also take the great circle around the back.
Perfect. So if I same example, but if I go the other way around, if I go like the wrong way, this in between these points, it's still a geodesic because, well, first of all, we saw it in the equations that it's like as long as it goes along the great circle, it's a geodesic, and in fact, it's not difficult to visually see that it is actually extremizing the thing. But in fact, if you now deform this to like, okay, this is a very bad picture, but okay, so suppose that instead of this I would take a curve which would go like, okay, I'm not sure if you know what I mean, but anyway, like you can try to take the geodesic and kind of move it around, and then it will get you can also shorten it. So yeah. Anyway, that should be a way to make it shorter actually. So geodesics are in general just extrema, not minima.
Is it obvious that it's shorter?
I thought so, but now I'm. Yeah, if you think of it, yeah. I think, let's do it this way. Okay, let's suppose that it actually goes along here. So it's like from here to here. I look at it like this. Kind of makes sense that if you deform it to go like this, it will be shorter. Okay, so I think from this picture it's.
That it probably will not be geodesic.
Oh no, it will not. It definitely won't be a geodesic. Yeah, no. It's just that.
Sorry, because I kind of blinked. Are we just producing the solutions, like guessing them, or are we proving that these are the only solutions?
I didn't prove anything of that sort. No, I'm just saying that there exists this functional, there is this functional and that functional. Both of them can be seen as functions on the space of curves, all curves, and that if I look at that function and I find the extrema of it, then in both cases these are given by geodesics. So I can, yes, so yeah, so they are extrema in the space of all curves. So if I deform the curve, No, that I don't require the deformed curve to be a geodesic. The claim is that these are extrema in the space of all curves. Okay, that's clear. Any other questions for my race?
What happens if we change power? For example, power 1.5, power 3.
Good question. Let's see. I think this is the. Okay, yeah, that's a very good point. I was wondering about it myself. So, yeah, I think it needs to be 1/2 or 1 because the claim is that if you have an integral of L dt, d tau, you have some extremizing conditions for it, and then you can have square root of L. Actually, okay, maybe I was too quick. Maybe it also works for, okay. Okay, I believe that as an exercise, but that's a very good question. I would suggest studying it in general, and then you can see it from there. Yeah, actually, it might hold for all of them, actually. Probably true for every. Because the function x will be different. That pop out here, I think. Interesting. Or maybe I'm wrong, but anyway. It's an interesting exercise, at the very least. Well, definitely for 0 it doesn't hold. This is intriguing. Very good. So this is the end of the geodesic section. Now there is a wonderful application of this, which is called normal coordinates. So geodesics can be used for many things. We will see for physical purposes why they are useful, or like why do they pop out. In mathematics, they're also useful in many ways, and one of them is these normal coordinates. Okay, so what's the idea here? So, as before, fix a pseudo-Riemannian manifold. Now, observation. For all points in your manifold, and for all directions in the tangent space of that point, all v in the tangent space there exists a unique geodesic. Again, a sequence of some basic ODE theory. Let me call this geodesic gamma v, such that it starts, the gamma v at point 0 starts at m, and its velocity is given by v. And okay, there is a geodesic defined on some. It doesn't have to exist at all times, but at least some epsilon time is enough. So this is essentially, for physicists, this would be a statement of like if you have initial condition, initial position and velocity, then you should be able to determine the curve. Okay. Okay, so okay. Let me stay with that. And then proposition is that there exists an open set U in the tangent space. So remember, this is a vector space. It's a space of all the directions in the point M. It's open. There is an open set which contains the origin. 0 is contained. Such that the following map, X, that goes from U to M, is defined by sending a vector to the corresponding geodesic and then evaluated at time 1. is a diffeomorphism. Between U and the image of the and any neighborhood of X, M in M. Yes?
Can you repeat why there exists a unique geodesic with those properties?
You mean why the observation is true?
Yeah.
So, where's the geodesic? Oh yeah, no, yeah. Well, the geodesic equation looks like this. It's so I think you can just use the usual ODE stuff, like you reduce this to like set of first order ODEs, and then because there is no singularity, whatever, multiplying this, then it should exist by.
I was just thinking, because on the sphere, you said that if you go along it,
Yes.
that's not a geodesic.
Yes.
But if I have a tangent vector that points in that direction,
Mm-hmm.
what would geodesic be?
Very good, very good. So yeah, so in fact the claim that I didn't prove, not even state actually, is that geodesics on a sphere are precisely in parts of great circles. So if you sit here and you try to go that direction, you know, and seemingly wanting to get something like this, and what you should indeed get is that, you know, imagine that this is your new North Pole and there is a South Pole opposite to it, and you go somewhere, I don't know, something like this. It's a terrible picture, but hopefully it conveys some idea. And sphere is nice because it's round, and so you always come back. So if you would deform the metric slightly, we would just like put some perturbation, then this is no longer true. You would just like go and wind around and whatever. Where was I? Okay, so what this thing says is that in fact these geodesics kind of go in all possible directions. So, okay, it says what it says. It's just there is a diffeomorphism between these things. Now, how can one use this? Definition: fix a point in the pseudo-Riemann manifold, and fix in the tangent space a basis and an orthonormal basis E mu. Okay, here you might ask, what does it mean to be orthonormal if the metric is not positive definite? And what I mean is just that the metric takes this form that you have like 1, 1, whatever, or -1, -1, 1, 1, 1, okay? It's diagonal with ones and minuses. So the natural generalization of what it means to be orthonormal for positive definite metrics. Okay. Okay, so pick these two data, a point and an orthonormal basis there in the tangent space. Then this thing gives you in particular coordinates on that tangent space. So just picking any basis in a linear space gives you coordinates on that space. So this gives you a linear basis, linear coordinates. On the whole Tm of M, right? Because any vector you can write as V is V mu E mu. And these things, functions, you can call coordinates. Okay, so picking a basis in a vector space gives you a basis. But now using this x, which I didn't say, but it's short for exponential, that exponential map actually gives you, via exp, we get a coordinate system in the neighborhood of that point. We get coordinates around the point M in M. Okay, so space, there was a point M, there was a tangent space. In that tangent space, we pick a nice orthonormal basis. And now this proposition ensures that actually there is a neighborhood of this point, which looks like a neighborhood in here. So I can use the linear coordinates induced by these vectors to cover the whole of this neighborhood. So there is some very nice set of coordinates around this point. These are called normal coordinates. This is not a very well-written sentence, but anyway, these are called normal coordinates. So in this setup, they are associated to a point and a choice of orthonormal basis in that point of the tangent space.
The proposition gamma is not defined for one.
I was hoping no one would notice this. Okay, yes. yes, okay, so there is a...
Or you can extend the domain of definition somehow.
Yeah, okay, so one claim is that it's... if it doesn't... Yeah, you can always make the neighborhood smaller, so that so this U, you can always shrink it. Because if you have a... if it's like... let's say you have a vector in the tangent space, and the geodesic is only defined up to like 1/2 or 2/3, let's say. Then you can go to you take, instead of that vector, you take only half of that vector, and that thing should live twice as long because it's, well, anyway, in other words, you can, okay, am I saying? Okay, I should probably put it as part of the sentence, that you can find a U small enough so that this is first of all defined, and it gives a, yeah, and the fact that it's defined, it really has to do that, you know, like it's a, like this U, you can imagine that it's like a ball, which is compact, and if you look at your ball, just pick any ball in here, in the tangent space, and you try to see, to every point in that ball you assign a number, which tells you how far you can extend the geodesic. And because it's compact, then that will have a minimum, sorry, minimum. There will be a minimal distance, and then you can just use that minimal distance to kind of, you know, make a smaller sphere by dividing some whatever, and then this thing will be well defined up to 0.1. So yeah, I mean, it's slightly more subtle, and I should have probably put this part of the proposition that there exists a U such that this thing is well defined, and that. Okay. Can I still use like 3 minutes? That's fine. Okay. There is the punchline. Okay, so why are these coordinates nice? Proposition in normal coordinates associated to some point M and this orthonormal basis. We have that the derivatives of the metric, of the components of the metric, are 0 at that point. Okay, so these are just some functions, and I'm saying that actually the derivative of these functions at that point around which we center the normal coordinates is 0. And one immediate consequence of that is that gammas are 0, because gammas, if you remember the formula, they only contain derivatives of g. So these are 0 at M. Okay, these are non-tensorial objects, so it makes sense that in some coordinates they are 0, in some coordinates they are not. But anyway, so this is the claim. And this is a super, super powerful thing to have, because then you can prove all sorts of, and this is where I will finish before the break. So this is an extremely useful thing in Riemann geometry. Even without constructing them, you don't really know what they look like, those coordinates. Just the fact that they exist is powerful enough to do some amazing calculations. So, example. So we didn't really discuss Lie derivatives, but if you take two vectors x and y, then the Lie derivative is another vector. And if you write it in coordinates, then what it gives you is this. The other way around. And now, a wonderful claim is that actually, this is the same thing as if I would replace all partials by nabla mu, following that convention that we had before. So what I'm saying is that this is the same as this thing. Why is this amazing? So this is amazing because this second expression, this is a tensor. This is like it's very clear that like each term separately is a tensor because, as we discussed before, this thing by definition is components of a tensor. So this is a great thing to have. Now, why is it the same? And the argument is that, okay, suppose that you have these two expressions. You know that both of these expressions are tensors. Here it's tensor because by definition these expressions were tensors. Upstairs it's less clear, but we know that this is actually just this and this is a tensor. So you have two tensors. And now pick any point and pick any normal coordinates around that point. And you know that around that point, well, gammas are 0 at that point. And how does nabla differ from mu? It's just nabla is just partial, and then there is some gammas. So you know that in the normal coordinates, at this point m, this thing is actually the same as this thing. So you have a tensor, you have another tensor, and you know that these two tensors in some coordinate system are the same. But since they are tensors, then they have to be same irrespective of what coordinates it shows. Because the tensor is a geometric thing, it doesn't depend on the coordinates. Hence they are equal, because they were equal in the normal coordinates, where partials coincide with nablas. Okay, and in the break you can try to, as an exercise, you can check that the Killing equations, which looked like this. Oh yeah, because I illustrated it in the case of x and y. You can, in fact, the same thing holds for a Lie derivative of any tensor. You can always replace all the partials there by nablas, and the same holds for exterior derivatives of forms. All the partials you can replace by nablas. You can think why, but I mean, it's the same argument. Essentially, the argument is that it only uses first derivative. And okay, in the exercise, you can check that these Killing equations, you can actually equivalently write them in a very nice way as nabla mu sin mu is 0. Okay, so these are the, remember this means symmetrization. You just write this using Lie derivative for this, write it replaced by partials and you get this. Okay, yeah, sorry for going over time. Okay, welcome back, those of you who have returned. Are there still any mathematicians in the room? Okay, good. Very good. Okay, so
Really, what was the question?
if there are still mathematicians in the room.
Yes.
No, I mean, I saw you. Okay. So I, in the last, what remains, I would like to. There is more things in the lecture notes, but I would still like to go over a couple of interesting things. Presumably something that could be interesting to mathematicians, and then I will finish with something that might be interesting to okay, so just so let me. I promise that I will make some sort of dictionary. Okay, let's go 3. So dictionary between physics and math. Yeah, this might be boring for physicists, so but then you can, you can add to what I'm going to say. So anyway, so what is the dictionary? How does all this? So far, this was Riemannian geometry. I didn't really talk about. I might have used some examples from physics, but anyway, this was a very mathy topic. So how does this relate to physics? Okay, so I suppose not every mathematician here has seen relativity before, is that right? Very good. Okay. So special relativity. Yeah, I've always felt about these subjects that they are actually made unnecessarily complicated because, like, the gist of it is actually just really simple if you know the math behind it. Maybe I was wrong, but well. So let me give you some sort of dictionary. So in special relativity, which is not the case we have, it's a more restricted setup without gravity. So what is your space-time there? Well, space-time, and that is Minkowski space. So underlying thing will be the physics lingo and the explanation. So this is just the same as to say that it's r to the 4 with the metric which looks like minus dt tensor dt plus dx tensor dx plus dy tensor dy dz tensor dz. We do it in 4D because that's, you know, kind of the conservative way of looking at things. You can generalize it to, you know, 10, 26, whatever you like. Okay, so note that there is a minus here. Okay, so the metric is of signature. Unfortunately, I will call it 3, 1. So there is like plus, 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 and there is a minus. But I will put minus first. Sorry about that. Okay, so this is what is meant by space-time. So now what does this really mean? This is the stuff that you should think of, like what does an observer see? So it corresponds. You know, you live in a space. You know, and this is what you see. It corresponds to an observer. What do I mean by that? Is that, okay, so for instance, points in here. Points in this Minkowski space, you refer to them as events. Why? Because simply, you know, I mean, if I draw a picture for this, ignoring the z coordinate, it's clearly the coordinate up is time. So a point in this space corresponds to something that happened at a precise point, okay, a precise xy coordinate, and it's on specific time. Okay, so it's something that happened somewhere at some point, so it's an event. That's how you call it. Now, if you have anything that's moving in this Minkowski space, then it's, you know, it corresponds to some curve. For instance, if you have a person sitting on his chair, not moving, that corresponds to a curve that goes upwards because he still moves in time. Right? This is a space-time diagram. So, movement of a particle or whatever, trajectory corresponds to a curve M. This is typically called the world line, if I remember correctly. In string theory, you have world sheets because you have a string that moves, and you know it cuts out the surface. It's called a world sheet. And if you have a brain, that's called the world volume. Now, the set of all vectors, so this is metric is not positive definite. There is lots of vectors which actually have zero norm. So there is lots of vectors which such that if you calculate their product themselves, then there are zeros. This thing is called the light cone because it corresponds to light rays. And the way in the picture, this looks like this. Yeah. So this corresponds to an observer sitting here, and these are kind of the lines in this, the straight lines in this light cone correspond to trajectories of light. Okay. Now, if you have something that's not light, but it's a massive particle, or like normal thing, something that has mass. These correspond to curves such that they stay within the light cone. So they move slower than the speed of light. So it's some curves that, you know, don't go like this, and they don't go outside of the light cone. So their norm is negative. Negative because the time component has a minus, unfortunately. Okay. What else do we have? Isometries. So what do the isometries of this correspond to? Isometries of M. So you can do it, well, you can check what are all possible diffeomorphisms of this space that preserve the metric. And this turns out to be the group SO. Is it 3-1 or 1-3?
They're isomorphic.
I know, but okay, let's say SO31 semi-direct product with R4. Okay, why semi-direct product? Because you can rotate them. You can make rotations. That's SO13, SO31, or you can make translations. And rotation acts on translations. So yeah, so there is a semi-direct product. So this thing is called in physics a Poincare group, I guess. Or some people call it a Poincare group. And this smaller thing, this guy, this is called the Lorentz group. Actually, sorry, I should have said just O, not SO. Was anyone complaining about this? No, no one noticed. Okay, so there was never an S there. So this is the Lorentz group. Okay, is it the T, or is there a T, or there are two of them?
Yeah, I think there's a T.
Thank you. Yeah, because there is also Lorentz with a Z in Lorentz gauge, I think. So, okay, so what do these things correspond to physically? So this thing corresponds, if you act with a group, then if you had a picture in one, imagine that you had some stuff happening, like for instance, you would have like a picture like this. Now you apply one of these transformations, and because of this weird extra non-positive definiteness, in a different, after applying this group, what might have happened is that this thing gets translated to something, okay, I'm not really used to hyperbolic, say, like this. Yeah, okay, thank you. So it might be deformed. So this would correspond to a transformation given like this, and physically you interpret this as change of observer. So this is changing observer. It's simply the viewpoint of a different guy. Now, how does this different guy relate to me? So if the relation between two guys was going through this R4, then that corresponds to the fact that the other guy was just sitting at rest with respect to me, but he was sitting somewhere somewhere, just like a different space or different time, whatever. So this is just translations. This corresponds to translated observers. So in terms of, yeah, in that picture, this thing would be just, to just move. Okay, move. Just move. Now, there is another thing which you might be familiar with. That's the SO3 subgroup of this thing. This O31. Okay. SO3 or O3, whatever. So this just corresponds to rotated observers. So this is rotated. This is just how other guys see this when it rotates. Okay. I should really rotate it in this XY plane. So okay. Artistic attempt to. Coming to the front, you see?
I'm a bit lost in translation. So you promised to underline physics, right?
Sorry?
You promised to underline what is physics.
Yes, then I stopped doing that.
Physics disappeared from the picture.
Sorry?
Physics disappeared from the picture.
Yeah, so, well, I don't know, physics. This is kind of the meaning of it.
Poincare is physics and Lorentz is not.
No, everything is. No, thank you.
Good that you underlined it in blue, because you would have complained.
So you assume I'm.
Okay, so now what else is in this group? So SO31 corresponds to these bits where it looks like this. But there is also, there is some stuff up there in this group O31. So what does that correspond to? That's where the, interesting stuff comes in. So suppose that, for instance, that this was kind of like case 1, case 2, and the case 3, the most interesting one, is that if you have elements that look like this, that 0, 0, 0, 0, 0, 1, 1, 0, 0, and something interesting happening here. So for instance, if you define this thing, where gamma is simply 1 over square root of 1 minus u squared, where u is some number. then transformation of this type corresponds to switching to an observer who is moving with a constant velocity. So this represents the observer moving with velocity u. And in this particular case, because I picked this metric, this would be in x direction. Okay, so this is where kind of special relativity becomes interesting, that actually once you have an observer that starts moving, then actually time and space become mingled between themselves, and and stuff happens. That's the end of the explanation. Yes?
Is this gamma different to those gammas?
Sorry?
Is this gamma different to the gammas of the paths?
Very different, yes. Yes, that's a completely different gamma. This one is, it's a different gamma. This is called the Lorentz factor, and that's a curve. Sorry. Yeah, there is only finitely many letters. It is in the alphabets I used, sorry. Okay, and one last thing in the dictionary. Actually, you will see that, okay, you will see. Last thing is that if you have an observer, which, if you sit in your comfortable origin and you see some other guy moving around, going around, whatever, presumably by staying within the light cone, then time measured by this guy that is moving, time measured by a moving observer, along some curve, corresponds to the length of that curve. So if I was moving if there is someone that is moving like from here to here, and I'm wondering, for me this was clearly, I don't know, time 0, and this was like time 3, whatever, some time. But if I'm interested in what will the watches of the observer measure, then they will the time that he will see corresponds precisely to the length. Now length measured with respect to the Minkowski metric. So, length. So not ordinary length, but that length with this non-positive definite signature. And as a sanity check, you can check that if you yourself are sitting at the origin and you are the guy who is moving, namely you are not moving and you are just going along the time direction, then the length here simply coincides with this t coordinate. So it matches, like, if you don't move, then really your length corresponds really to this coordinate. But once you start moving, it becomes weirder. Like the famous twin paradox that, there's two of you, one of you just sits at the point, and this is your world line, and there is a second person who goes away in a rocket, and then comes back, and then you measure these two things, and it turns out actually that the length of this curve, which corresponds to the time that really passed for this observer, is actually smaller than this one, because of this weird minus in the metric. If you calculate it, then the length of this blue one is less than the length of the white one. That's the so-called twin paradox. Okay, so yeah, this is a short dictionary between the notions, if you ever see this in physics. Yes.
Sorry, isn't the velocity u that you've written upstairs, up there on the table, the relative to the speed of light, or is it just a velocity?
It's just so in this setup, this is the velocity as measured with respect to you who are standing in the.
Because in the formula, like you've written down, I remember there was also c in the formulas.
Oh, you mean like the speed of? Oh, yeah. Yes. Okay. Good point. In all of these things, c equals 1. Yes, this might look like a weird thing, but it's just actually a perfectly normal thing to say, because usually you have some units after that, and the units are kind of arbitrary. So you can choose units in which c equals 1. It's like a perfectly legit thing, so I don't know what the fuss is about for some people. Yeah, thanks, that's a good point. Okay, now a corresponding dictionary with GR is actually much simpler, because once you accept special relativity, then GR is just special relativity with Riemann manifolds. So the dictionary here is much shorter. Now relativity. Sorry? Okay, so this only has 4 terms. Okay, so first of all, what is space-time in this? The place we all live in. From the viewpoint of general relativity, this is a Lorentzian manifold, so Riemannian manifold. With a metric of signature 3, 1. If you believe we live in 4 dimensions, as some people do. Sorry, yeah, this thing, usually you have more stuff in space-time than just space-time. So you can have some fields, you know, electromagnetism, whatever, some other stuff. So you can have some with other geometric objects, with other geometric structures potentially, that you can call matter. For instance, if you would study electromagnetism, then you would have a 1 form living there, or something like a 1 form. So just, but the important thing is that it's just some other tensors, typically, or sections of some bundles or whatever. Okay. Now, this is not anything. It cannot be any wild manifold, so this has to satisfy something. So this satisfies so-called Einstein equations. I will come to them in a second. So far, just remember Einstein equations. So far, this is just, you know, some equation. Minkowski space is a particular solution. Now, second point is that test particles, where by test, what I mean is that it's something very small that doesn't curve the space-time around itself significantly. You know, it's something light like a person or a planet or a galaxy or a dust or something. So these move along geodesics. At least, I mean, if there is no other. I mean, as far as the space-time itself is concerned, they move along geodesics. If you have additional fields, okay, so the particles move along geodesics. That's just an important statement. And then maybe another thing, normal coordinates. Correspond. What's called a freely falling observer. So this is kind of the most basic observer, the most basic type of observer. He just like floats around and has no engines or anything. It's just like falling in a black hole or somewhere. And the stuff that he sees around him, that's kind of one of the ideas of the general relativity, is that locally at the best approximation, everything looks like Minkowski space. So remember the normal coordinates, actually, the derivatives of the metric are trivial. So the metric actually looks like this metric, the diagonal one with, yeah, this one. Call it G0. And then nothing in the linear order, and only it starts at like, it's like, it starts in the second order. So up to the lowest approximation is just Minkowski space. And this is what you see when you are freely falling, you know, in a black hole or whatever. Then the stuff around you in a small neighborhood, it really looks like it's not curved. And you can only see the difference once you really start being careful and look at the corrections to your geometry. Okay, and one last thing, and the last thing is, okay, now, there's this point. Time measured by moving observer corresponds to length, let's call it sharp. So this thing survives in GR. Okay, so yeah, that's the dictionary. That's the basic one. Any questions for that? Yes?
So you said how time can be measured by moving observer, so how space is measured by moving observer?
Good question. How does this go? I guess it maybe makes sense to, if you're falling down, then at each point it probably makes sense to consider like a plane that's perpendicular to your movement.
If you can measure time and you know c, this time of, I mean, if you use light and you know how to measure time, you also know how to measure space.
Well, I mean, concretely, it's like, what would be the numbers? I guess you can...
You take a laser and you measure the time it takes to travel from A to B. It gives you the distance between A and B.
Okay.
This is how we define the meter, right?
I mean, yes. I thought it's something like this. Like once you have a curve, then you can sort of make a. You can make a system around it like this, right? You just look at the spatial plane perpendicular to that, and then you measure things in respect to that. Anyway, it's a thing that I should be able to answer. Maybe someone else can answer. Yeah. I mean, one thing that I should say, it doesn't answer your question, but like one thing is that if you're really interested in coordinates, not in these normal ones, but really like a finite region, not finite, but like, okay, put differently, there is, so the coordinate systems in GR are very arbitrary. There is no like Minkowski was very clear that it's a very nice form of the metric and it's globally applicable and everything. In GR, it's mostly, if you really want to describe your full universe with some set of coordinates, then it's usually just some arbitrary set of coordinates that you choose. Okay, yeah, I don't know how persuasive that was, but yeah, I can try to. We can discuss later. I will try to remember. Take the plane, and this is your new coordinate. Something like that. Okay. Where was I? Okay. Oh yes. So Einstein equations. So now, what are these famous equations that these stuffs that the universe is supposed to satisfy? So, right. Chart 4 or something. Okay, so you've before seen the idea that like in fact I think Olga said this, right? That the matter tells space-time how to curve and the space-time tells the matter how to move. So the second part is this thing, that you know that matter moves along geodesics typically. But also the presence of the matter, if there is a lot of the matter, it affects the space-time itself. So there is some relation between the two things. So schematically I want to write down an equation that looks like as follows. So some curvature stuff equals presumably some numerical constant, kappa, times some matter stuff. Okay, I want to make this precise, but this is kind of the idea that you see. You have like some curvature quantity, that purely from Riemann geometry, and the way this behaves is that this is affected. This is affected by the presence of matter in some way. Now, okay, so now what is this? How do I make this precise? And you will see that there is essentially only one thing to do this, roughly speaking. Okay. So physics tells you several things. First thing, it supplies a very nice candidate for the right-hand side. This candidate right-hand side, namely, there is a thing called the energy-momentum tensor. So there exists a particular tensor, energy-momentum or stress-energy tensor or other names of tensor. For us, it's just a tensor. It has two indices down, and it's symmetric, and it satisfies this identity that, okay, I'll put it up. It's divergence free, so this is just a statement that if I take the covariant derivative and then contract, then this is 0. And and it's known from physics that if you have some particular type of matter, then you know all these things. This is like a good candidate for the right-hand side. Now, what about the left-hand side? What can we put there? So, well, another from physics tells you that you usually should look at things that are up to second order in derivatives of the field. So, up to second order search for something that's up to second, search for stuff which is up to second order in derivatives. What does that mean? So the field in here is the metric, and so I want to have some left-hand side which only contains the metric, its derivative and its second derivative, but I don't want to go beyond that because then I might, it's not a good idea. So, okay, all of this just boils down to saying essentially that the only candidate you have for here is just something that also has two indices, like this thing, right? And it's made out of the curvature tensors, Riemann, Ricci, scalar, which I didn't stress it, but they are second order in derivatives of the metric. Okay, so what are the possible candidates that you can cook up? Okay, yeah, maybe any suggestions from people who've never seen this before? You have these three tensors. You also have the metric. And what are the possible expressions that you can cook up that I can put in here if on the right hand side I put this t mu nu? So what possible constructions can I use these tensors to? I want to have an equation that this equals t mu nu. So what can I put on the left? Any ideas from these things? Very good. Ricci tensor. Let's put some number in front of it. What else?
The metric.
Very good. We'll put that as the last one. Metric. Some coefficient. I will call it C. Which might be a hint of how many things are missing. What else? I'm allowed to multiply things. It's not just, Can do it.
Scalar curvature.
And it needs to have two indices. This has two indices, this has two indices, this has two indices.
So you multiply it with the metric.
Yes. Very good. Okay? It can be, sorry. Mu. Yeah, okay, so it can be either Ricci, it can be scalar times metric, or it can be the metric. If you try to cook up anything else, then you will fail. I mean, the only other contraction that you can never get anything else from here, which has two indices, that's not Ricci. So this is the only thing that you can do. Okay, now, can I constrain these coefficients in any way? Well, first of all, I didn't tell you what this constant was, so I can just, let's say I divide everything by A, I absorb it in this constant. Okay, you may ask what happens if this is 0, yeah?
Could we contract like two Riemanns, or at least three indices from like two Riemanns to get like a two index double curvature tensor kind of thing?
Aha, okay, I see that the issue there would be that it would still be second order, but there would be like more there. Like there would be like powers of the second order. That's okay, so good point. So I should add here, it's not just this, but we also want there to be just the second derivatives, I don't want higher powers of second derivatives. Second derivatives times second derivatives, that's not good. The Riemann has...
Einstein's equations are nonlinear.
Sorry?
But aren't Einstein...
They are not linear, but they are... No, they are not linear. But they are still linear in the second derivatives. Should be true. Is that true? Yeah. That is definitely true. Yeah. I mean, the Christoffel symbols are like metric derivative of that, and then the curvatures are essentially Christoffel symbols and derivatives of Christoffel symbols. Yeah. So they are yeah. Yeah. Thank you. Okay. So you see that it's slightly more subtle than
the scalar. The scalar curvature is the derivative of a Ricci, of a Christoffel times the metric. No, because you contract it. So like G, like the Ricci itself is already a derivation on the Christoffels.
Yes, and this one as well. This is also second order derivatives. Second order derivatives of G. Because Riemann was, and this is just algebraic contractions of it.
So you basically mix G times second order derivative of G.
Yeah, that's fine. That's still fine. Yeah. Thanks. Okay, sorry. There is more subtleties as you see, but anyway. let's just stick to this one. Okay, so I got rid of one constant, so there is three more. Now, okay, now I need right-hand side satisfies this. So it would be, I mean, if I want to have an equality like this in general, it would be better if this left-hand side was satisfied as well. So let me call it left-hand side in mu nu. So, well, then it would be great if I could have some condition like this. Now what happens if I substitute this for e mu nu? So I get a covariant derivative of the metric, which is 0 because the derivative is, the connection is Levi-Civita and it automatically preserves metric. But there I will have some nasty expression of like this guy hitting this and this guy hitting the Riemann, the scalar curvature. And here I will use something that I have not derived, but I saw it in the exercises in the preceding sheet, so I will in the preceding V series. So I will. Okay, so there is a thing called the contracted Bianchi identity, which is, I will just state it and not prove it.
And the first coefficient was 0. I mean, you asked.
Yes, yeah. This could have been 0. In that case, I couldn't do what I did. And I just presume that for some reason that's a bad theory, but I don't know.
But you don't satisfy the
You don't satisfy the
freeness, right?
Well, maybe I put this one to 0 as well.
Okay.
Okay, but no, that's a good point. So the second condition actually will tell you that A cannot be 0 without B. Good point. I should have maybe swapped the order. Okay, yeah. So there is this thing called the contracted Bianchi identity. This is this thing. And using this thing, you can show that this thing happens if and only if this coefficient B is equal to -1/2. So, our final form of the equations, and these are the Einstein equations, is R mu nu -1/2 scalar curvature times the metric. And unfortunately, we were not able to constrain this in any way. So I will just keep it and I will call it lambda. Okay, so these are the Einstein equations. These numbers, so this number, real number, is called the Einstein gravitational constant. And this thing here is called the cosmological constant.
Could you show again the equation, the lower equation? Yeah, this.
Yeah, if you add Nabla on it, you can use this one and you will get a term which looks like this, and they combine it. Okay. Just one last statement in here before I wanted to do the final remarks. Okay, so. Okay, so this is the set of equations. So there is, in fact, a very nice variational approach to this. You can obtain them as Euler-Lagrange equations for some stuff. And this is called the Einstein-Hilbert functional, and I should really mention it because it's important. Einstein-Hilbert functional. This is defined as follows. You pick a metric, and then you calculate the following quantity. You take, okay, conventionally there is some coefficient, 1/2 kappa, and then scalar curvature, and if you want to have this cosmological constant, you should also subtract 2 times lambda. And you integrate this over your manifold, and there is one thing I didn't say, but probably maybe you heard it before, is that if you have a Riemannian manifold and you pick an orientation on it, then there is a natural volume form. So in a sense, there is a natural way to integrate functions. And it was found long ago by Hilbert, I think, that actually varying this, you would get precisely the left-hand side here. So I mean, what I mean is like the extrema of this functional are given by left-hand side being equal to 0. And to get the full Einstein equations, so Einstein equations are Euler-Lagrange equations. So extrema for the following thing, for the Einstein-Hilbert action. That's to recover the left-hand side. And then whatever you need to put that governs the behavior of your matter fields. So if you have, this is some matter fields. For instance, it's one form if you talk about electromagnetism. So this is just a second bit that you need to pick depending on what theory you study. And the dictionary is then this T mu nu is defined as -2 over volume of G of partial derivative of S matter with respect to anyway. So there is a nice variational principle to derive all this. There is in the lecture notes I put discussion of examples. Okay. So if you're interested, what does it mean to have a de Sitter space, anti-de Sitter space? What is a black hole? What is a rotating black hole? What is a charged black hole? What does our universe look like? Like what is the cosmological form? Then you can look there. It's kind of just one page. So I won't discuss the examples, but there is one thing that I promised to say. How many minutes? I still have 5 minutes? That was very easy. Do I have 15 minutes? Okay, so there is this last bit which okay. I will not give it any title. You will see what it is. So, well, one claim in here is that if, okay, an observation is that if lambda is 0 and t is 0, so if there is no matter, you would call this vacuum, then the equation looks very simple. It's just this thing minus this thing is 0. But in fact, you can show that the Einstein equations are equivalent to the saying that the Ricci tensor is 0. Okay, this uses the fact that the dimension of m is not 2. In 2 dimensions it doesn't work. But anyway, you can show this. It's very easy by just tracing the equation. So what I'm saying is that the Einstein equations in vacuum are just so much simpler. They just say that the stuff is Ricci flat. The Ricci tensor vanishes. Okay, now you can suppose that you have you have some solution to these vacuum equations, and you try to perturb your metric. So suppose that you have a metric such that Ricci is 0. Now you try to perturb it. So you write G plus some small perturbation delta G. Okay, and delta G is very small. Then there is a relatively, actually not that, but I needed some hints. But anyway, so there is you can check how does the Ricci tensor changes. And there is the following beautiful formula. Okay. In terms of this delta G. Okay, let me call it H. That's, I think, the usual thing. This is small. H mu nil minus 1/2 nabla mu nabla nu H rho rho plus, here I will write some symmetrization on this thing. Like this, and then plus stuff that's like H squared. So I'll put the low, sorry. Okay. So here indices are raised and lowered using G. Okay, so this thing is really, I use H and I raised it using G. Okay, so it's just a relatively nasty looking expression, but okay, so there is kind of two things you can do with this. So first of all, you can now realize that actually if I study perturbation of this metric, then not all metrics that look different are actually different, because I can have a diffeomorphism. I can have I can just relate two space-times if they are diffeomorphic, and I mean I can just perform change of coordinates, and I should still regard the metric as being physically equivalent. And change of coordinates would result in applying a diffeomorphism, and actually it would change the metric. So there is a freedom, is what I'm saying, that allows you to identify H with H okay, with H, which looks like this thing, where for some vector field that generates your diffeomorphism. So there is in fact some physical equivalence. So you should really see this perturbation to be the same as this one because they just refer to different choices of coordinates. Okay, so there is some freedom. Now it can be shown, and I won't show because of time, that it can be shown that actually you can use this freedom and you can pick your vector field in such a nice way that you can restrict your H to satisfy the following equation. This is called gauge fixing. Okay, so what does this mean? This is your infinite dimensional space of all possible metrics that you have. Now some of them are equivalent, they just correspond to change of coordinates. So there is some orbits of this diffeomorphism group. So this is like physically equivalent things. I'm drawing them by line. And gauge fixing just means that I impose like a transverse slice. I impose that there is like a consider only metrics that satisfy this thing, and and hence I will only consider these things living in these blue things. But if I do that now, if I only consider metrics of that type, then the equation above simplifies because these things will drop out in this gauge. You can check. Like, sorry, not here. No one complained. So yeah, assuming this gauge, this equation simply becomes this. Okay, and there is now two things to finish. One implication is that, well, suppose that this G that you started with was the Minkowski metric, the flat metric, the easiest thing that you can have. Yes, sorry.
I was just wondering about the gauge fixing. For example, in QFT, when we take the Lorentz gauge, we do the kind of the cut with the orbits, but we still have some some redundancies left. We haven't fully fixed the gauge. Yes. And I wondered, does that sometimes happen in GR as well? If you pick some gauge where you don't necessarily fix all of the things, all of the...
I would say probably, but probably. I mean, you can have at least isometries of G, which would be like trivial here. I guess that's it, maybe. Probably isometries are the leftover symmetry. Anyway, let's think about it maybe later. Yeah, okay, so the thing number one, if G was Minkowski, so the flat metric, then these nablas simply become partials, and then what I have here is the wave operator. So then this thing will be simple rho H nu. And since I want this to be 0, sorry, there was another partial, I have a wave equation. So you see that the perturbations of the Minkowski metric, they just form, they have to satisfy a wave equation, and these are the famous gravitational waves. So the small metric perturbation, the way they propagate through space is that they have the form of a wave. So this is why these are gravitational waves. Okay, let me just stop there. And the second bit, which I find very intriguing, is that, and this relates to this famous Ricci flow, is that suppose that you have your manifold, and suppose that you have a one parameter class of metrics, so depending on some parameter, let's say lambda. Not just one metric, but a whole curve of metrics, some continuous parameter. Now you can consider the following equation. G derivative of lambda is minus 2 times Ricci. For the metric G and lambda. Okay, so this minus 2 is there simply to offset this thing actually. And what you see that this is a horribly nonlinear equation because the way Ricci tensor is formed out of the metric is very nonlinear. But up to this first approximation, and in this gauge, this right hand side looks like a wave. The right hand side roughly, taking the minus 2 into account, looks like a wave operator, or like Laplace operator, whatever, acting on these metric perturbations. So what I want to say is that up to, if you squint your eyes and look at this, this looks like a heat equation. Here I'm secret, I didn't say this here, assume that G is really Riemannian in order for this to make sense.
There you have a variation of R menu, and here you have just R menu.
Yes. Yes, but okay. So the way you should look at it is that if you see this as an equation for H, like you fix your G and you look at this as an equation for H, then this thing is really like Ricci for this whole thing is like Ricci for this guy plus. Plus
I see this.
Okay, so the punchline is that this is very nonlinear, but in some sort of weirdest, very small first order approximation, this thing actually looks like a heat equation if G is Riemannian. And so this fact can be used to prove some very powerful theorems. So this is if you heard about the program of Hamilton and the proof by Perelman of the Poincare conjecture, then this is what's been used. Namely, roughly the idea is that you pick a manifold, you put a random metric on it, and then you let it evolve. And you might know that the heat equation, if it were just a heat equation, then the heat equation has these nice smoothing properties. So for instance, if this would be a two-dimensional surface, and you put any Riemannian metric on it, you can show that under this thing, which is called the Ricci flow, the metric would just flow until it in infinity reaches a metric of constant curvature. So it starts with something very random, spiky, whatever, and then it nicely flows into something round as much as possible. Unfortunately, this only holds in 2D. In 3D and more, there is singularities that develop, and as far as I understand, Perelman was the one who showed how to deal with the singularities, like proved some conjectures of Hamilton based on this kind of thing. And that, as a corollary of that, was the famous Poincare conjecture. But yeah, you can see it. Yeah. Well, for us, it really ties to the story in this way. And incidentally, in string theory, this is the renormalization group for string sigma model. So that's another connection to the story. Thank you very much for your attention.
So probably we have time for a short question.
I have 1.5 questions. Is it permitted? So I used 1. So if I look at your story about matter and metrics that talk to each other, that sounds like biting itself by its tail.
Sounds like what?
Sounds like they bite itself by its tail. Right? So like,
yeah.
As a mathematician, so should I look at this as a condition on what given what? Like what is my input data, what is my solution that I search?
So, I guess it's easiest in this variational approach. It's like if you want to look at possible configurations that you can have, then those are configurations that minimize this thing in all the fields, so in metric and in the matter field. Or alternatively, the universe is supposed to obey this equation, and then there is additional equations for the matter fields that correspond to their own dynamics.
But then I should put some constraints on it, because otherwise I get an empty universe flat and I'm happy, right?
Seconds, right?
So I need to impose some conditions on it, not just saying I extremize this, because if I do, then I just get the empty universe which is flat.
Well, but I mean, you are supposed to put in the matter action as well.
Yeah, I say no matter.
Okay.
And I say G is constant. Then I'm happy, it's a solution, right?
I mean, G is constant is probably not a well-defined thing, but...
Oh, okay, up to that.
I mean, yeah, then the equation would be that it's Ricci flat. Okay. And anything Ricci flat is in principle admissible.
Okay, and then the real question is, mathematically it is well-defined, right?
Sorry?
And mathematically it is well-defined.
To do... Sorry?
To solve this variational problem.
Oh, yeah. Yeah, I mean, the equations are just this. So to solve them is a different issue.
No, I mean, solving, yes, you see, it's a nightmare, but like at least there is existence, uniqueness in some sense.
Well...
But there's not uniqueness, right? You can have Minkowski, like you say, flat, but then there are solutions which are not flat.
No, but I mean, you can have some starting conditions, like, so you can pick some evolution, you can have some slice, and you have some, like, like, you say how roughly, like,
yes.
velocity, and then you can wonder about
I see,
that.
I
and
see, I see.
There should be some statements. It's a bit hyperbolic because of the minus, so it's a bit tricky, but yeah.
Yeah, that's what I'm trying to say. So.
Aren't in certain circumstances there is a unique solution like the Schwarzschild if you have like spherical symmetric?
Yes, that's also true. That's also one of the examples that if I had like another couple of hours, it's in the sheet. If you assume what is it, spherical symmetry
and it's
and
static,
the vacuum, the Schwarzschild
it has to be static too.
I think that follows from the. I think that's like this. Someone's theorem. Yeah. Right. So spherical symmetry in vacuum is enough to imply Schwarzschild.
So if there's no other questions, let's thank Fridrich again. And